Hi, my name is Neil. Thank you for joining me in my storage room, which turned out to be my temporary office during those crazy times. And thanks for coming to hear about my work, which is entitled Deep Soft Interference Cancellation for MIMO Detection. This is a joint work with Long Fu from Tsinghua University and with my awesome mentor from Weizmann, Yonina Eldam. The work is about MIMO communication and specifically about uplink multi-user MIMO systems where a set of transmitters are communicating with a single multi-antenna receiver. Now, this is obviously a very common model in wireless communications and in cellular communications, where we have a base station which serves multiple user terminals, and the number of users and the number of antennas can be very, very large, as in the massive MIMO regime, and this problem is the focus of considerable research over the recent years. Specifically, we discussed the most basic problems in the context of communication, which is symbol detection. Symbol detection means that there's a transmitter which wishes to convey information to a receiver. Unfortunately, they're not collocated. There's some channel in between, so it has to transmit a set of symbols, and the receiver has to decode those symbols to detect them from its observed channel output, which may be noisy, which may be corrupted. Now, obviously, this problem has been well studied for decades. There is a multitude of algorithms which are capable of recovering the transmitted symbols S from the observed Y with proven optimality and with controllable complexity, depending on the specific characteristics of the channel. And they usually assume that this channel, the statistical relationship between the output and the input, are known and typically simplified as in a linear Gaussian format. And once we have this conditional distribution, we can just plug it into our favorite symbol detector algorithm, favorite symbol detection algorithm, and to get our results. However, these algorithms, they usually assume, well, one, the channel model is usually simplified, which means that it does not necessarily reflect actual channels. And it also has to be known, which means that it has to be repeatedly estimated, inducing overhead. Finally, model-based algorithms are typically sensitive to uncertainty, meaning if we do not know the channel accurately, if we have errors in our knowledge of the channel, the performance may deteriorate considerably. So we want to put aside this model dependence, and we can note that recent years have witnessed a very growing interest in machine learning methods. It has emerged as powerful model-independent tools, and we can ask whether we can use deep learning to remove channel model dependency in symbol detection. And the answer is, yeah, obviously, we can just replace this big symbol detector with a deep neural network. Well, yeah, the thing is here that we need a lot of parameters, which means that we need a lot of training in order to tune this neural network. Now, communication channels change rapidly, so it means that we either need to retrain it oftenly, or we need to train it over a large set of different channels, which means that the network will not be optimal for either. And essentially, this end-to-end deep network approach essentially ignores what we've been doing for centuries in communication and signal processing. So we want to somehow combine deep learning and model-based symbol detection, and we will do so by model-based deep learning. So in this work, we will see how model-based deep learning can be used to facilitate symbol detection in uplink multi-user MIMO systems. So in this talk, I will begin with a few words of how we see model-based symbol detection. Afterwards, we'll discuss on its specialization for the problem of MIMO symbol detection, and we will look at the family of interference cancellation algorithms as the one which will be the focus of this talk. And then I will show how you can implement a data-driven interference cancellation-based receiver using this proposed tool. So model-based deep learning refers to the usage of deep learning, of deep neural networks, for problems which can be tackled using conventional model-based algorithms. So there's a conventional way to do that. It's called deep unfolding. It's been studied quite widely over recent years, and it looks at problems where one would typically solve using this iterative optimization algorithm, which consists of some iterative processing. Now we want to implement it in a data-driven manner. So what deep unfolding does, it first writes each iteration one after the other, and then replaces each iteration with a dedicated layer of a neural network which tries to imitate the operation of this layer. So what we have in the end of the day is a deep neural network which is inspired by the algorithm. So we essentially integrated the algorithm into our design of the deep neural network. What we're proposing is somewhat different. Instead of integrating the algorithm into the deep neural network, we're proposing to integrate the deep neural network into the algorithm. What we're proposing to do is to identify the specific computations of the iterative algorithm which depend on the channel model, and to use dedicated compact machine learning methods in order to replace those computations, inevitably allowing the complete algorithm to be carried out in a data-driven manner. Now, this approach has been used in some applications. For example, it is the underlying rationale of plug-and-play networks and of recent works on deep priors and deep regularization. But here we focus specifically on symbol detection, and we actually have done some previous works on the application of this approach for model-based deep learning for symbol detection. We have shown how it can be used to implement Viterbi detection, which is the maximum likelihood sequence detector for finite memory channels. And we also used it to implement the BCJR detector, which is the maximum posteriori probability detector for the same family of channels. Now, these algorithms, what they actually do, they just take the symbol detector. Instead of using prior knowledge of the channel, they simply replace the part where this channel knowledge is needed and use a dedicated machine learning method to do that. Okay, so we can use those previously proposed works, but the thing is that both Viterbi and BCJR algorithm, regardless of their data-driven implementation, are more suitable for scalar symbols. But what we have in MIMO, well, in multi-user MIMO, which is our problem of interest here, well, we have the receiver has a very large number of antennas, and furthermore, we don't have a single user, we have multiple users, and the complexity of those algorithms grows exponentially with the number of users. So neither Viterbi nor BCJR should be the way to go in this problem. So we want to ask which symbol detection algorithm one should use here. And this brings us to the discussion between separate and joint decoding. So the optimal thing to do in uplink MIMO communication is to do joint decoding. I need to use the channel output in order to recover all the transmitted symbols simultaneously. Unfortunately, this is unbearably complex. The complexity grows exponentially with the number of users. So what is usually done is what's called separate decoding, in which we recover each symbol separately while treating the rest as noise. This is the main approach in massive MIMO literature. It does lead to some performance loss. We actually, in a previous work from TCOM from 2019, we quantified how suboptimal it is in the massive MIMO regime. And there's also something between separate and joint decoding, which is what's called interference cancellation. Interference cancellation means that we code each symbol separately, but we use the other detected symbols to facilitate the recovery of next detected symbols. So it's somewhere between joint decoding and separate decoding, and it balances performance and complexity. In particular, under the family of interference cancellation method, there's the set of what's called iterative interference cancellation method, which simply recover all the symbols and then use those recovered symbols to facilitate the same recovery all over again and do it in an iterative manner. There's a problem here of error propagation, because if we have misdetected one symbol, it will affect our ability to recover the remaining symbols. So what was proposed about 20 years back is to use soft symbols, what's called soft interference cancellation, which means that we use the channel output in order to detect each of the symbols, but instead of producing a hard decision, we're producing soft decision, namely a conditional distribution of the symbol. And then we use those estimated soft symbols to facilitate the recovery of the next symbols and do so in an iterative manner. So that's the soft interference cancellation algorithm. And well, as being a model-based algorithm, it does require to know the channel in order to do this soft detection. And also, in order to do interference cancellation, to remove the effect of the remaining symbols, what we need is for the channel to be linear. We need the effect of the interference to be linear such that it can be canceled in subtraction. So these are two limitations we wish to address, and we wish to address them using deep networks. And how do we do that? Well, let's first examine the basic building blocks of iterative interference cancellation. And those building blocks consist of this block which cancels the interference from the channel output based on the previous estimate. And there's another block which uses this interference canceled estimate in order to recover the current symbol. So when we look at it, we see that each block, its inputs are the channel outputs and the postulated conditional interference distribution. And the output is the conditional distribution of the current symbol. So what we actually have here is some sort of a classification task, right? Because we have a set of inputs and we're trying to estimate a conditional distribution given those inputs. So this is actually quite naturally implemented when using classification networks with softmax output layer trained to minimize the conditional entropy. They are essentially what they output is the conditional distribution of the label given the input. So what we propose to do is to simply replace those basic building blocks of soft interference cancellation with classification deep neural networks, which look just like what we have here. Now, how you train the whole thing? Well, the basic approach would be, well, we now have a deep network architecture. We can just train the whole thing in an end-to-end manner and just minimize the sum cross entropy loss. Namely, just look at the final outputs and to minimize their as a set of classifiers with respect to the symbols, which are the labels here. Now, the problem here with this approach is that we train the whole network simultaneously. So we essentially have a very large network, a large number of parameters. So in order to adapt them, we would need a large training set. So what we can do is account for the fact that we know what each building block does. We do not have to just look at the output of the network. We know exactly what each building block does. Each building block has to estimate its corresponding symbol. So what we can do, we can just train each building block individually and do it all in a sequential manner. And then we can use the same training set to train each building block, which means that we now train using the same training set a much smaller number of parameters using the block-wise cross-entropy loss. And then we can just use a much smaller training set in order to train the overall network by accounting for the purpose of each one of those building blocks. So if we look at a numerical example, we look how it behaves. So we first consider a relatively small channel, a 6x6 linear Gaussian channel, because for this channel, we can actually estimate the best joint estimation, the map rule, which is this red curve here. The blue curve here is the model-based iterative soft interference cancellation algorithm, which knows the channel. And then you can see this purple curve and the green curve, which are the performance of our proposed deep soft interference cancellation method. And as we can see, it's within a very small gap from the model-based approach, depending on whether the training is carried out in a sequential manner or in an end-to-end manner. It's also much, much better than this orange curve here, which is the performance of an unfolded receiver, what's called DetNet, proposed in the work by Samuel et al. From 2019. And that one required 100 times more training in order to achieve this performance, which is within a gap from the performance achievable using our algorithm, which essentially implements soft interference cancellation in a data-driven manner. Now, the performance becomes even more notable, the performance gain, when we look at uncertainty. When we have uncertainty in our knowledge of the channel here, model-based algorithms perform quite poorly, both the map and the model-based soft interference cancellation algorithm, while our deep network-based algorithm perform similarly well as if they were trained using perfect training. So as we can see, we actually learned to implement soft interference cancellation, and we are much more improved to uncertainty compared to model-based approaches. Now, we also see the same results when we go to much larger channel. This is a 32 times 32 channel, where we can see that our deep soft interference cancellation method achieves roughly the same performance as the model-based iterative soft interference cancellation algorithm. And we also achieve similar performance when we do training in a sequential manner and not in an end-to-end manner. Now, these are all linear channels where soft interference cancellation, the model-based version, works. We can also look at a Poisson channel where it's not a linear channel. So the soft interference cancellation really doesn't work. It cannot cancel the interference by subtraction. However, our proposed deep soft interference cancellation method works very well with uncertainty or without uncertainty, with end-to-end training and with sequential training. So this actually demonstrates the gain of using deep networks here. So in this talk, we presented a data-driven implementation of the soft interference cancellation method. We did this by combining machine learning algorithm into channel model-based methods. Specifically, we showed that soft interference cancellation is a reliable and scalable mammal detection algorithm, which can be extended into a data-driven implementation, which we call the deep soft interference cancellation, DeepSIC, by learning to cancel the interference from labeled data. And we showed that it is applicative to nonlinear setup, and it is robust to CSI uncertainty. And we showed notable gains over previously proposed deep MIMO receivers. We actually hypothesized that this architecture can also be used for multitask learning, because in the end of the day, we are estimating multiple symbols. So that was my talk. I want to thank you for listening. I want to invite you all to see our paper, to check out our paper on arXiv, which is available on this link. You're more than welcome to check it out. Also, feel free to contact me if you have any questions, and do enjoy the remainder of this wonderful virtual conference. Thank you very much.